Welcome back to the Algebraic Graph Theory seminar. This week, Sarah Plosker is here to tell us about centrosymmetric stochastic matrices.
Thank you, Max. This is joint work with Lei Cao and Darian McLaren. Darian was an undergrad student at Brandon University, and now he's doing his master's at Waterloo. And Lei Cao, I met just kind of randomly at an AMS sectional meeting, and he was giving a talk on some of his work on different kinds of symmetries related to doubly stochastic matrices. And then I was asking, generalize this at this meeting. And then just sort of through the coffee break, we were chatting, and then it wound up turning into collaborations. So that is what I love most about conferences. And I hope this summer with the virtual conferences, it's not quite the same, but maybe it'll be almost as good. So let's get into it. So just so we're all on the same page, I'll define a stochastic matrix. This is my notation I'm using. This is an M by N real matrix with indexed by these entries Aij. It's stochastic if the entries are non-negative. And this is my notation. I don't know if it's actually saving space or not, but it looks kind of like it is. It's the square brackets just mean the indices 1 through m and the indices 1 through n. And then the summation overall, each row is 1. And if you want column stochastic, you can just take the transpose. And a square matrix is doubly stochastic if the entries are non-negative, and each row sums to 1 and each column sums to 1. And the convex, so the set of all doubly stochastic matrices, n by n, is convex, and it'll be denoted omega n. And the set of all stochastic matrices that are m by n, this is convex, and it's denoted by gamma mn. Okay. So we're talking about convex sets. So immediately we want to know what are the extreme points. And there's the famous Finkhoffs Theorem for doubly stochastic matrices. So omega n is the convex hull of the set of permutation matrices and n by n permutation matrices. So permutation matrix is just a 0-1 matrix with exactly 1, 1 in each row and each column. So the extreme points of the doubly stochastic n by n matrices are the n by n permutation matrices, Pn. So you can ask what are the extreme points for stochastic matrices? And I think it's intuitively clear that the extreme points for stochastic matrices should be what I'll call rectangular permutation matrices. So exactly 1, 1 in each row, because we're talking about row stochasticity, so we don't really care about how many ones are in each column. The extreme points of n by n stochastic matrices are precisely the rectangular permutation matrices. And I was talking with various people, and they all agreed it was clear, but nobody could provide a reference for this. I think maybe it's a standard problem in a grad course, so you don't want to put the proof out there. I don't know, or the proof is pretty clear anyway. But just for sake of clarity, we'll go through an example. The proof is kind of ugly just because you're dealing with generic terms. So you have all these indices that kind of don't really do much to clarify things. So let's go through an example. It's basically using Hall's marriage problem. What's an extreme point? So you have I didn't notice the chat until now. Exactly. So you have a convex set. So a convex set means that for any x and y in that set, if you draw a line between x and y, you don't go outside of that set. So I don't know, like the letter C or something, if you have an x here and a y down there, you draw a line in between them, that line goes outside of the letter C versus like a circle or a triangle or something like that. Okay. Ooh. Yeah, the corners, yeah. Yeah, exactly. So if you, the only way to write a convex combination of any elements in that set, and by convex combination, I just mean a linear combination where the scalars are between 0 and 1 and they sum to 1, then the only way to do that is sort of trivially being that all of the scalars are 0 except for 1 with that same yeah, sorry, I don't have a tablet. I ordered one and I wish it had come for this talk, but it hasn't arrived yet. But yeah, if the only way to write a convex combination, or sorry, if the only way to write that element as a convex combination of other elements in that set is just trivially with zeros everywhere except for a 1 for that element. So x equals 0 times y plus 0 times z plus 1 times x, then that's an extreme point. So there's no way of writing sort of the corners of a triangle as convex combinations of other entries of that triangle. I don't know if that makes sense. I wish I could draw a picture. Sorry?
It's all very clear. Thank you. It's very
okay. Great. So these extreme points are very important because through the extreme points, you can sort of almost recreate that set. And so that's the great thing about convex sets. So we want to write, so this is some matrix that is 3 by 4 and it is row stochastic. So the entries of each row sums to 1 and they're all non-negative. And we want to write it as a convex combination of rectangular permutation matrices. So what we can do is randomly select a positive element from each row. You can select the leftmost one, the rightmost one, the biggest one. I think here I chose the largest one. And if there were entries that were the same, I took the leftmost one. You can do it randomly, but that's how I chose to do it, not exactly random. And then what you do is you subtract a row permutation or a rectangular permutation matrix that has ones in the same positions as the selected entries. So I selected the 1/2, 7/10, and 2/5. So there's a 1, 1, and 1. And then 2/5 was the smallest number among those three entries. So I subtract off 2/5 times this matrix, and then I divide by 1 minus 2/5 just to re-normalize everything so that it's still, the resulting matrix is still stochastic. And it has fewer positive elements than A. This A1 has a 0 here now, where there was that 2/5 there. So it has fewer positive elements than A. And then what I can do is keep doing that. So I select, let's say 5, 6, 1/2, and 2/3. So there's a 1, 1, 1. 1/2 is the smallest of those entries. So I take A1, I subtract off 1/2 times this E1. I divide by 1 minus 1/2 just to get the resulting matrix A2 to be stochastic. And there's fewer positive entries. And I keep doing that. I select, here I selected 2/3, 1, and 2/3. So 1, 1, 1. I subtract off 2/3 times this E2, and I divide by 1 minus 2/3. And then my resulting matrix A3 is actually a rectangular permutation matrix. So I can stop at that point. And then I can just take these equations and rearrange. So I can solve for A here in terms of A1 and E0. And I can take A1 here and solve for A1 in terms of A2 and E1. And A2, I can solve that in terms of A3 and E2. And so I can write A in terms of E0 and A1. I can replace A1 with this combination of E1 and A2 and so on. And then I get A written as a convex combination of these rectangular permutation matrices. So these rectangular permutation matrices are the extreme points, or it follows that the rectangular matrices are the extreme points of the stochastic m by n matrices. So that was the extreme points for stochastic matrices. So the other part of my title involves this type of symmetry. So I wanted to talk about symmetry. So a square matrix, an n by n matrix A is symmetric if it's equal to its transpose. So Aij is equal to Aji. So it's symmetric about its diagonal. And a square matrix is Hankel symmetric, also called persymmetric or mirror symmetric, denoted A equals A to the H, if Aij is equal to A n minus 1 plus n plus 1 minus j, n plus 1 minus I. And what that means is symmetry about the anti-diagonal. So that's how you can visualize it. And for centrosymmetric, we can actually use a rectangular matrix. It doesn't necessarily need to be square. And we denote a matrix that's centrosymmetric. We say A is equal to A the pi, pi being 180 degrees or pi radians. And in terms of the indices, Aij is equal to A m plus 1 minus I, n plus 1 minus j. So you've sort of swapped these indices a bit. And what it is symmetry when rotated about 180 degrees. So you can actually write down your matrix on a piece of paper and twirl your paper 180 degrees, and that's your new matrix. And if your matrix is stochastic and symmetric, or stochastic and Hankel symmetric, then it's automatically going to be doubly stochastic. And Lei Cao and his collaborators had already sort of worked on that. And so the only thing new would be to look at, well, there's other generalizations, of course, but we can look at stochastic plus centrosymmetric. And that'll give us something new that that Lei hadn't already did. So that's what we were looking at. So centrosymmetric stochastic matrices. And we want to look at extreme points. So remember, gamma mn was the stochastic m by n matrices. Now we're putting this pi to mean centrosymmetric stochastic matrices. And we're trying to characterize the extreme points. So one lemma we can say is that all extreme points can be written in this form, 1/2 r plus r to the pi, where r is a rectangular permutation matrix. So the proof is very quick, so I'll just give it. So because A is a stochastic matrix, we can write it as a convex combination of the rectangular permutation matrices, because we characterized, remember, the extreme points of the stochastic matrices are the rectangular permutation matrices. So yeah, convex combination, so the CIs are non-negative and they sum to 1. But A is also centrosymmetric. So A is equal to A rotated by 180 degrees. And so we can actually just rotate each of the rectangular permutation matrices by 180 degrees and the convex coefficients stay the same. And then we just average them, and A, because it's centrosymmetric, it's equal to A pi. And so A is equal to 1/2 A plus A pi. And so then it's just this convex combination. So the C1, C2, etc. are still the convex coefficients. And now the matrices are the 1/2 R plus R pi, 1/2 R1 plus R1 pi, 1/2 R2 plus R2 pi, etc. So this is the form that they have. But we want to say a little bit more in terms of characterizing them. So the next lemma we have is that if we have a rectangular permutation matrix and m is an even number, we'll see this will play a role later or throughout the talk, really. If R is not centrosymmetric, then there exists an m by n centrosymmetric rectangular permutation matrices Q1 and Q2 such that R plus R pi, R is not centrosymmetric, so this isn't equal to 2R, is equal to Q1 plus Q2. So two distinct centrosymmetric rectangular permutation matrices. And I will give an example rather than a proof. It's nothing too illuminating. So this is, let's say, 4x4 matrix R, and it's not centrosymmetric because either this third one here should be here, or this second one should be over here to make it invariant when you rotate by 180 degrees. So if you take r plus r pi, now it is centrosymmetric. And the entries can either be 0, 1, or 2. If they're 2, you can just split them, and both Q1 and Q2 have 1s in those same spots. And if there's 1s, then you kind of just divvy them up so that there's exactly 1, 1 in each row for each of the Q1 and Q2. And so these two matrices now are centrosymmetric and stochastic. Okay. So that was for M even. The interesting thing for M odd, if M is odd and N is even, we might have extreme points containing 1/2. So for example, this 3x4 matrix S, this is stochastic and it's centrosymmetric, but there's no way of getting rid of those 1/2s. If you deleted one of them, and yeah, I mean, there's just no way of getting rid of the 1/2s without compromising the fact that it's stochastic or without compromising the fact that it's centrosymmetric. So we'll see these 1/2s popping up whenever M is odd. Yeah, so we have a lemma. So M and N, M has to be even. N could be either even or odd. For M even, then we don't have this 1/2 case popping up. So we can actually characterize the extreme points precisely. So based on what we know so far. So an M by N centrosymmetric stochastic matrix is an extreme point of that set, if and only if it's a centrosymmetric rectangular permutation matrix. So basically exactly what you would hope for. So the extreme points of doubly stochastics are the permutation matrices. The extreme points of stochastic are the rectangular permutation matrices, and the extreme points for the centrosymmetric stochastic when M is even are the centrosymmetric rectangular permutation matrices. For M odd, we basically have to delete that middle row. That's the problem row. And then that new matrix is a rectangular permutation matrix. So if R is an M by N rectangular permutation matrix, then 1/2 R plus R pi is an extreme point of the centrosymmetric M by N stochastic matrices, if and only if either M is even, and then R is a centrosymmetric rectangular permutation matrix, and then 1/2 R plus R pi is just R. So R is an extreme point if and only if M is even and R is centrosymmetric rectangular permutation matrix. If M is odd, then we have to look at R tilde, which is M minus 1 by N, centrosymmetric rectangular permutation matrix, where we've deleted that center row from R. So if we ignore that center row that has the 1/2s, then we can just say, well, then we're in the M is even case, okay? Okay, so we have the extreme points, and then we want to look at basis. And so, okay, so for M by N stochastic matrix, if we have N minus 1 entries in a row, that other nth entry is fixed. We know it because we know that the sum of the rows has to be 1. And this occurs for each of the M rows. So the dimension of this space or this set is m times n minus 1. And we have to be careful because this is an affine space, not a vector space. So just in terms of counting, a basis for the m by n stochastic matrices would contain m times n minus 1 plus 1 linearly independent vectors. So we have to add that 1 just because we're not actually dealing with the vector space. So we're looking for this many linearly independent vectors, and then we know that that would be a basis. Okay, so how do we do that? Well, this is our construction that we're using. Okay, so we have Ci. This is a 0, 1 matrix with all elements being 0, except all the elements in the ith column are all 1s. So Ci has 1s in the ith column, 0s everywhere else. And then these Bij's are 0, 1 matrices, where the ijth entry is 1, and then all entries in the j plus 1th column are 1, except ij plus 1th entry, which is 0. All other entries are 0. I don't think that made any sense, so I will go to what I mean by that. Okay, the Bij's has 1 in the ijth entry. Okay, B11 has 1 there, B21 has 1 in the 2-1 entry, B31 has 1 in the 3-1 entry, and so on. I didn't have space to do B41, B51. B12 has 1 in the 1-2 entry, and so on. And then all entries in the j plus 1th column are 1. So in the second column, they're all 1, except the ij plus 1 entry. So all that means is where that 1 is in the ijth entry, you have a 0 in that j plus 1th column. And then all the other entries are 1. And then here we have a 1 here, so we have a 0 here, and then all the other entries are 1. And here we have a 1 here, so we have a 0 in the next spot over, and then 1s in that all the other entries. And so this only actually goes to j up to n minus 1 because we're not sort of cycling back. So yeah. Okay, so Ci has all 1s in the ith column, 0s everywhere else. Bij has this form where 1 in the ijth entry, the next column over has all 1s except that corresponding spot, which has a 0. Okay. These matrices, B11, B12, et cetera, B21, et cetera, up to Bm, n minus 1, and Cn, so 1s in the nth column, are linearly independent. And there's the right amount of them. There's m times n minus 1 plus 1 of them. So that's a basis for the stochastic m by n matrices. Okay, so we have a basis for the m by n stochastic matrices. It's not too hard to show that they're linearly independent. You basically just need to argue that the 1s only show up in certain positions for certain Bij's and the Cn, and so yeah, it's not too hard to argue that they're linearly independent, and then there's exactly the right amount of them. Okay, so what do we do for a basis for the centrosymmetric stochastic matrices? If m is even, it's kind of the natural thing to do. You take a basis for, so if m is even, so 2k, let's say, then you just look at the basis that we just created for dimension k. So you replace m with k, and then you plop that in at one of those basis elements as the sort of first block of your matrix, upper block of your matrix, and then below that, you just rotate that matrix by 180 degrees. So you do xi as a basis element, and xi rotated by 180 degrees, and plop that in as your second sort of block immediately below, and then that'll automatically be centrosymmetric. And there's the correct number of them, and they're still linearly independent. So that'll be our basis for the M by N stochastic, centrosymmetric stochastic matrices. So you just take the basis for half that amount. So if M is 2K, you just look at the basis that you just created for K by N, and then you stick that as the first block, and then the second block, just rotate by 180 degrees. Okay, so if M is odd, so 2K plus 1, we're going to look at N even or N odd. We just have to, I mean, this is just saying how many there are, because again, you just have to sort of make sure that they're linearly independent and make sure you have the correct number of them, and then you have a basis. The CI, the ones in the ith column, zeros everywhere else, is just is the same thing, but it's going to be K by N, so it's no longer square. That's okay. So if M is odd, you have this basis where the CI tildes, you take the CIs, so ones in the ith column, zeros everywhere else, and then you rotate 180 degrees. So you have CI up top, the CI pi in the bottom, but you have to stick in this middle vector with 1/2 in 2 spots, the ith spot and the n minus I plus 1 spot. All the other entries of that vector are 0. So it's kind of, ignoring this di, it's kind of exactly what you would assume, but then you have to stick in this middle vector with the 1/2. And then the xi's are defined similarly, the xi's coming from that same sort of basis that we looked at, where you look at, instead of 2K plus 1, you look at the K by N basis that you created here. And then you stick that in, you stick in the 180 degrees rotation at the bottom, and then you have this middle row again. The middle row is either that same 1/2, 1/2 in there, or it is, and that's for N even, or if N is odd, it's just a 1 in the L plus 1th entry. So mostly the even case is just exactly what you would expect. The odd case is almost exactly what you would expect, except you have to deal with that middle row. So just a basis for the 5x4 centrosymmetric stochastic matrices, you see that there's these 1/2s popping up in the middle row. Okay. We also looked at graphs associated to these matrices. So we have the extreme points, we have a basis, and we looked at graphs associated to the matrices. Sorry, and so we look at a bipartite graph, where so a bipartite graph being you have 2 vertex sets. One corresponds to the rows R1 through Rm. The other vertex set corresponds to the columns S1 through Sn, and an edge connects Ri and Sj if and only if the entry of your matrix is non-zero, basically. So we have a bi-adjacency matrix associated to the constructed bipartite graph. And the graph corresponding to a centrosymmetric stochastic matrix is also centrosymmetric in that if there's an edge between vertices Ri and Sj, well, that happens if and only if there's an edge between vertices Rm plus 1 minus I and N and S n plus 1 minus j. Okay, so centrosymmetric matrix then gives way to a centrosymmetric graph. Okay, and so then we just sort of reinterpreted our results in terms of these graphs. So we have an extreme point of the stochastic M by N matrices if and only if the associated bipartite graph is a forest, and the degree of all row vertices is 1, or equivalently, all row vertices are leaves. And that implies that the sum of the degrees of all column vertices is m, and that there's no path longer than 2. And that's just sort of an immediate sort of graph theoretic consequence of, or interpretation of our results. And I'll get to an example in a minute, but I just wanted to give the graph theoretic interpretation of the result for centrosymmetric. So if M is even, it's exactly the same as the previous corollary. But if M is odd, then you have to deal with that middle row possibly having 1/2 in it. So P is an extreme point. So if M is odd, P is an extreme point if and only if the bipartite graph is a forest and the degree of that middle row vertex is either 1 or 2. The degree of all other row vertices is 1. And so that 1 or 2 just corresponds to, there's a few basis elements that that didn't have the 1/2, they just had a 1 in one of the entries. And so then that would correspond to the 1 here, but the ones that have 1/2, 1/2, then there's 2 different, yeah, the degree would be 2. Okay, so if we have this extreme point here, then the corresponding bipartite graph is, so R1 is connected to S4, R2 is connected to S4, R4 is connected to S1, R5 is connected to S1, and then there's this middle row here, R3 is connected to S1, column 1, and column 4. So hopefully this graph there, well, it should be a forest. The degrees of all the rows vertices are 1, except for that middle one is 2. And there shouldn't be any path longer than 4. 1, 2, 3, 4. Yeah, we can get up to 4, but there's no path longer than 4. So with these graphs, one thing that we did was we looked at this graph parameter called the fill of a graph. It comes up quite a bit in social network analysis, so it gives some indication of global connectivity of a graph, and it can be defined for general graphs, but specifically for a bipartite graph, it has this formula here. So the fill of G is equal to the size of the edge set divided by the size of the first vertex set, and the size of the times the size of the second vertex set. So this gives the probability that for 2 randomly chosen vertices, there's an edge between them. So we can calculate the fill of the graphs corresponding to all of the various matrices that we looked at, all the basis elements, all of those, you know, the CIs with the 1s in the ith column, the BIJs that had that strange kind of form, and we can compute the fill. It's not very illuminating, other than I will note that for centrosymmetric M by N stochastic matrices, where M is odd and N is even, it has a larger fill because of all those basis elements with that, because of that one middle row with the 1/2s, because there are 2 different non-zero entries in that row that basically boosts, well, it increases that edge set count by 1. And so I don't know really what this means exactly for social network analysis. I was kind of joking that, well, somehow if you have an odd number of friends, somehow you're more connected than if you have an even number of friends on Facebook or what have you. I don't know. But it did seem like it was a parameter, a graph parameter that was very much of interest to sort of more computer science, big data people. We can also look at the faces of the M by N stochastic and M by N centrostochastic matrices. For doubly stochastic matrices, they're characterized by the permanent function. And what they are, so you let K be a subset of indices ij, and you construct a 0, 1 matrix that has 1 in the ijth entry, if and only if ij is in that subset of indices k. Then the face associated to that matrix is capital F of B, and it's all x, all m by n stochastic x, that such that it's entry-wise less than or equal to the corresponding to the matrix B that you're looking at. So you fix 0, 1 matrix B, and all stochastic matrices that are entry-wise less than or equal to B are going to be in your face. So we can characterize that. So we have the vertices are precisely the rectangular permutation matrices, so the extreme points that are entry-wise less than or equal to the fixed constructed matrix B. And to determine all the non-empty faces, you can actually matrices having row support. So what that is matrices B such that if one of the entries is 1, then there exists a rectangular permutation matrix P such that the corresponding entry is either 1 or is less than or equal to that entry. So all I mean here is that we don't really care so much about the faces that are empty, right? This is some set of all x's satisfying some condition. If there's no x's that satisfying that condition, that face will be empty, and we don't really care so much about those faces. So we're going to sort of ignore those ones when we actually go to construct these faces. So we're only going to construct these non-empty faces. That's all I mean when I say that. Okay, so I'm going to look at, I'm going to use this notation AI dot to mean the row sum. So the dot just means I'm summing over all j's. Yeah, I don't know. By now, maybe you notice that the indices just, if I can avoid indices, I do, because I don't like them. So the number of vertices of a face where B is without loss of generality, this 0, 1 matrix having this row support. So the number of vertices in a non-empty face is you take the row sum of the first row and you multiply that with the row sum of the second row, multiply that with the row sum of the third row, etc. So you're multiplying over all I of the BI dots, where BI dots is the row sum. So I'll do an example. So the number of vertices of a face of this matrix here, this row sum is 2, this row sum is 2, this row sum is 1. So you do 2 times 2 times 1. So there should be 4 rectangular permutation matrices that are entry-wise less than or equal to this matrix. And there are exactly 4 as expected. So these are the 4. Okay, so we want to look at the faces of centrosymmetric stochastic matrices now. And before, to deal with the non-empty faces for stochastic matrices, we just had to look at certain rectangular permutation matrices. Those rectangular permutation matrices, remember, rectangular permutation matrices are the extreme points of the stochastic matrices. For here, we have the extreme points being, well, we have sort of this block structure with the one block up top, and then we rotate it 180 degrees and put that as the bottom block. And then if M is odd, we have that middle row that might have these 1/2s. Okay, so those are going to be the extreme points. And so when we're looking at non-empty faces, we have to look at extreme points that are entry-wise non-negative, or sorry, entry-wise less than or equal to our given matrix B. Okay, so we have some given matrix B. It's a 0, 1 matrix, and we're going to look at the number of extreme points that are entry-wise less than or equal to B, extreme points of m by n centrosymmetric stochastic matrices. If m is even, then we just have to do the row sums, and we have to multiply them together up to k. So m is equal to 2k. You just have to take the top half of your matrix and just multiply those row sums together. If m is odd, you have to, sorry, I just have to mute myself. Sorry about that. Didn't want everyone to hear me cough real loud. So you take the row sums up to not quite half. So half, but ignore that middle row. So k minus 1. You multiply those row sums together, and then you take the k plus 1 row sum, you divide that by 2, and you take the ceiling and you multiply that. And that is how many vertices of your face you have. So that might sound kind of strange, so we'll do an example. Okay, this is 3 by 3, and let's first consider the case where this middle entry is 0. So our row sums, the first row sum is 3, the second row sum, let's say, is 2 for now, and the third row sum we don't really have to worry about. So if m is 3, so this is 2 times 1 plus 1. So we actually don't have anything to multiply here. We just row sum. So that is b1 dot, so that's 3. 1 plus 1 plus 1. And then we multiply it by the second row sum. So k is 1, so 1 plus 1 is 2. So b2 dot divided by 2. b2 dot, we said, is 2. 1 plus 0 plus 1. Divided by 2 is 1. We take the ceiling, it doesn't matter, so we have 3. And working through the extreme points of the 3 by 3 centrosymmetric stochastic matrices, we see that there are precisely 3 that are entry-wise less than or equal to B. So these are them. And they would be rectangular permutation matrices except for this row of 1/2, that middle row. Okay, so if C is 1, then we have row sum is still 3 for that top row, but now we have a 3 here for the row sum of the second row. So 3 divided by 2 is 1.5, and you take the ceiling, so you round up. So you're going to get 2. So 2 times 3 is 6, and there's actually 6 extreme points that are entry-wise less than or equal to B. So we looked at, basically, moral of the story, for centrosymmetric stochastic matrices, if M is even, we can sort of get by with the stochastic case. If M is odd, so we just have to look at, for M even or odd, we have to look at sort of half of that amount, and then do a 180-degree rotation, plop it down as the sort of second part of our matrix. And then for M odd, we have this middle row that might have 1/2 in it. That kind of, well, messes things up, but it makes things actually more interesting. And so we looked at extreme points, bases, the graphs associated to them, the fill of the graph, and these faces. And normally, so I know in this seminar series, a lot of people are looking at quantum state transfer. And normally I would give a talk on that, but this project was just kind of a, not really related to quantum graph theory or quantum state transfer. It was just kind of a fun sort of linear algebra graph theory project that I guess the centrosymmetry would be the only thing that I think could maybe be applicable. At least it kind of sometimes pops up in quantum state transfer, or Hankel symmetric or mirror symmetry typically comes up in the quantum state transfer with respect to, let's say, quantum state transfer of, or perfect state transfer of paths, or mirror symmetric trees with the weights had to be mirror symmetric. So this is kind of, I'm trying to make connections to quantum information, but it's sort of 6 steps removed. So this was mainly purely just a pure math for fun project. So that's really all I wanted to talk about. So thank you very much.
Thank you.
And saying centrosymmetric stochastic matrix over and over is just a mouthful. So
Yeah, I was impressed. I only said it once right at the start, and I thought, oh, wow.
Oh, I think there's something in the chat. Oh. So yeah, I guess there's other ways to generalize this that we might keep going with the project in different ways. Yeah, there's, yeah, like, oh, sorry.
I was just wondering, like, other symmetries that you would look at, or more with
so I don't know that there's other symmetries, just because for the most part, the other symmetries plus stochastic give you doubly stochastic, and then that's already sort of been looked at. But there's other ways to generalize, like there's doubly stochastic, then you generalize to stochastic, then you can generalize to sort of substochastic, or then you can get into sort of connections with majorization theory. And there's all sorts of different matrices related to majorization that you can look at.
I guess one other question I had, or one question I had, I don't know if it's probably not a good answer to this, but so if you think about the Birkhoff polytope geometrically, and then you try and imagine, you know, one of these, like the polytope you're getting for one of these centrosymmetric guys, say you've fixed some large n, and you're looking for, your rectangle is now, like one of the parameters is n, and you're varying the other. So I'm wondering if, like, the geometry of the Birkhoff polytope and the geometry of where things sit in this polytope are related in any interesting way, or if
Yeah, I don't know off the top of my head. They certainly should be, I would expect, sort of the same. Like all the linear algebra shows you're sort of doubling things, and then you have maybe this middle row to look at, but sort of you can get like the basis and the extreme points and stuff through the basis and extreme points of stochastic. So, you know, the geometry, surely there should be kind of an analogous, I don't know. I don't know too much geometrically speaking, so.
me either.